the current through this inductor will force this thyristor to conduct beyond angle pi. So that is why we will obtain a negative peak at output as well. And if you see that the current corresponding to this output waveform will start from this angle alpha and will continue to charge up to angle pi. But when at pi, this voltage and the current both should have dropped to 0. But now we have inductor in our circuit, and the energy stored by this inductor now needs to be released in circuit as well. So the current will continue to this thyristor T1 will be in reverse conducting mode because of the negative cycle, but the current from this inductor will force this thyristor to keep on conducting and will discharge its energy completely up to this angle pi plus beta. This angle beta is known as angle of extinction. If we see at the voltage waveform across this silicon control rectifier, we will obtain a waveform something like this. For time interval 0 to alpha, when the gate of this thyristor was not triggered, whatever the input voltage was, it started to develop across this thyristor and is shown here. And now when the negative cycle arrives, we discuss that the conducting angle of this thyristor has increased from pi to pi plus beta. Hence the voltages, the voltage waveform will be something like this. That is from pi plus beta to 2 pi. So this part of the waveform across this thyristor is due to the negative or the reverse cycle of the input sinusoidal signal, and this is due to the, and this part of the waveform is due to the forward blocking mode of the thyristor. That is when the gate was not triggered. And now if we want to calculate its average output value, it can be derived using this formula, that is integrate it for its this quantity or its conducting time period. Here we have considered that the angle of extinction beta is equal to alpha. So that's why we are integrating from pi to pi plus alpha instead of alpha to pi plus beta. So whichever notation you like, you can continue in that. So if you see, the final result obtained is something like this, and this angle alpha, the trigger angle, it can be varied from 0 to pi by 2. So if we see that is this at this formula, we conclude that the average output value has now decreased, because at cos 0 it will be have its maximum value, but at any other angle alpha is equal to 0, this will keep on decreasing. Now if we see the analysis of an RL load with freewheeling diode, this is our freewheeling diode, this is our sinusoidal source, and this is our thyristor, and this is our RL load. The waveforms that we will obtain in case of freewheeling diode will be something like this. This is our input signal, this one, and if we this is our triggering instant, alpha is equal to 45. This is our control signal. So when this gate is triggered at this specific time interval, alpha is equal to 45. So our output voltage starts to follow its input signal. You can see here. And now this is the current I0 obtained at output. So you will see that due to the use of this freewheeling diode, our current, our load current is not reaching to its zero value. Hence we can say that it is in continuous conduction mode. Whereas in absence of this freewheeling diode, we saw that the current through the load was reaching to its zero value. But now we have selected some specific higher value of this inductance, and due to the impact of this freewheeling diode, now this inductor will be in continuous conduction mode. That is, our current is not dropping to the zero. And now if we see at the waveform obtained across this thyristor, it is something like this. This part is due to the fact that we have not triggered our thyristor for this instant 0 and from 0 to alpha angle, and the voltage waveform appeared across this thyristor in the negative half cycle is from pi to 2 pi. Since now this although we have an inductive load in our circuit, it is not causing this thyristor to extend its conduction angle, but it is causing or using this path that is being provided this freewheeling diode to release its energy. So